Chapter 2 deals with chemistry, and of course we have to talk about chemistry because most physiology is based in chemistry, and because chemistry, the last two levels, the molecular, atomic level, are both levels that we need to understand in chemistry so we can understand these levels of organization. Everything in the universe can basically be boiled down to what we call matter and energy, and matter is basically, our definition, anything that occupies space and has mass or weight. And matter is made up of atoms or elements. And energy is basically the ability to do work, which takes many forms. And of course, the body is made up of both matter and energy. So to break the body down into its lowest common denominators, we need to understand these. Now, energy is often transferred from one form to another. So in the body, we see all of these basic forms of energy. Chemical energy we see in the form of things like glucose, C6H12O6, fructose with the same chemical formula, and adenosine triphosphate. As a matter of fact, we convert glucose to adenosine triphosphate by its breakdown, and when we do that, there's never 100% efficiency when you're converting from one type of energy to another. But at the same time, as we know from the laws of physics, that energy can neither be created nor destroyed, but has to be changed from one form to another. So when we're changing energy from the form that we eat it in, as a form of glucose, and to this form that we can use it in the cell as ATP, then where we lose the efficiency of the breakdown, we lose the energy. Instead of energy being destroyed, then we lose it in another form, and that would be the form of radiant energy, which we call heat. Now, we've already said that muscles produce more energy, or produce more heat than anything else, and the reason why is because they use more energy than anything else, and then that transfer of energy from our carbohydrates to ATP, then we're going to lose part of that inefficiency as radiant heat energy. Now, we also have something very similar to electrical energy, and maybe you've heard, and obviously you have heard, of things called nerve impulses, and we will properly call them action potentials. So we'll talk more about that later on, but that is almost a form of electrical energy, the movement of ions. We even have the movement of electrons through electron transport systems within the mitochondria. So these are very similar to what we would consider to be electrical energy. Mechanical energy is actually the energy of movement. Of course, we're going to mainly see mechanical energy in the contraction of muscles. Of course, matter is made up of elements, and atoms are the building block or the expression of the elements. So we give the elements different chemical symbols, such as carbon has C as a symbol, oxygen O, hydrogen H, nitrogen N. And carbon, hydrogen, and oxygen actually are found in all of our organic molecules, nitrogen also being found in specific organic molecules such as proteins and nucleic acids. Good thing is, those four elements actually make up 96% of our body. So we need to know something about that, since we're going to be mostly made out of those four elements. There are some other elements that we'll also be talking about, but we only really need to know a handful of elements compared to how many there actually are. Atoms are actually made up of two major areas. We have a dense area in the middle called the nucleus, and then we have an area outside of the nucleus that is basically an electron cloud full of orbiting electrons. Now, the nucleus is further broken down into positively charged particles called protons and negatively charged particles called neutrons. The electrons that are orbiting the outside electron cloud are basically negatively charged. We need to understand these factors, and for the atoms that we are concerned with, we can see that the number of protons will equal the number of electrons, and most of the time the number of neutrons will also equal the number of protons. Carbon is the backbone organic molecules in the backbone of living structures. So let's look at some of the characteristics of carbon. Here's a carbon atom. Notice that we have 6 protons and 6 neutrons in the nucleus, protons being positively charged, neutrons being neutral. We have 6 electrons in the orbitals around the nucleus. So notice that the electrons are placed in different orbitals. We actually have 2 electrons in the inner orbital, and then in this case, since there are 6, we have 4 left over in the outer orbital. So our atomic number is actually the number that describes and identifies an atom. So notice that our atomic number is 6, and the atomic number, again, is the number of protons, and this number never changes. If this number changes, then our atom changes. So our atomic number is the number of protons, and it does identify the atom. Atomic mass happens to be the number of protons plus the number of neutrons. This number can change because we can have different isotopes of the same atom. As we said before, the atomic number is the number of protons, and that's really what identifies the atom. And the atomic mass is the number of protons and neutrons. This number can vary according to the different atoms and their isotopes. Isotopes, as we see in this slide, are actually the same, or atoms with the same atomic number. Therefore, that identifies them as a specific type of atom, but they vary in their number of neutrons. So they are variations of the same type of atom. So looking at our picture, we see common hydrogen, which actually only has 1 proton and 1 electron, no neutrons. We see an isotope of that. It also has 1 proton, therefore it is still hydrogen. But in this case, we have 1 proton, 1 neutron, and 1 electron. And then we see another isotope where we still have our atomic number of 1, only 1 proton, again identifying the atom. But in this case, we have 2 neutrons, and we still only have 1 electron in each case. So isotopes, again, have the same number of protons, but they do vary in their number of neutrons. Atomic weight being the number of protons and neutrons, and knowing that isotopes vary in the number of protons and neutrons, means that the atomic weight will be determined by whichever is the natural isotope variation, whichever one occurs most. The other numbers, and we usually, for most things except hydrogen, the variation usually, if we have a higher number of neutrons and protons, then it tends to decay, becoming radioactive. So most of the time, we're going to have the natural isotope variation for most things being the one that has the same number of protons and neutrons, hydrogen being the exception to that. And of course, radioactivity comes from the fact that when we have isotopes and we have more neutrons and protons, then it tends to become unstable, and so the neutrons will decompose, and as it decomposes, it releases energy, and the energy is basically radioactivity. Atoms tend to combine with other atoms to form both molecules and compounds. Now, a molecule can actually be 2 or more alike or different atoms that are combined chemically, whereas a compound is always 2 or more different atoms combined chemically. Atoms come together because they actually form bonds with other atoms, and so they can either come together by forming these bonds, or those bonds can be broken and they will then dissociate. Now, there are 3 major types of bonds we're going to talk about: ionic bonds, covalent bonds, and hydrogen bonds. For bonds to occur, and the reason bonds occur is because of something called the octet rule, which we're going to discuss. So we talked about where are electrons in an atom, and we know that they occupy different, what's called energy levels, within something called electron shells. We know that there are 2 electrons that can occupy the closest shell to the nucleus, and they are the most strongly attracted. So they would fill up the first shell before they would form in the outer shells. Each shell does have a distinct property, and every shell basically has an upper limit to the number. Now, the first shell can only hold 2 electrons. The shells outside of that, as far as we're concerned for what we're dealing with, can hold up to 8 electrons. As a matter of fact, they would like to have 8 electrons in their valence or outer shell. So bonding occurs whenever the atoms are trying to fill that outer shell that would like to have 8 electrons. So we call that outer shell, again, the valence shell. And if something already has a full outer shell, then it's not going to form bonds with anything else. Therefore, we would say it is chemically stable. If something does not have the outer shell full, then we say it's reactive, because it will want to react with something else to fill that shell. In order for atoms to bond with other atoms to form molecules, then they want to fulfill the octet rule, also called the rule of 8. Now, the rule of 8 basically says that the first shell closest to the nucleus can hold 2 electrons. Once it has 2 electrons, it is full. The shells outside of that can hold up to 8 electrons, and then whatever our outer shell is, which is called our valence shell, will want to have 8 electrons. Looking at our 2 examples here, we see that helium, which has 2 protons, 2 neutrons, and 2 electrons, is very stable because our shell is full. The other atom that we see here, neon, is also very stable, and these stable atoms, we say they are inert because they don't want to bond with any other atom. And the reason is, looking at neon, notice 10 protons, 10 neutrons, also 10 electrons. So we have 2 electrons in the first shell and 8 electrons in the valence or outer shell. Since there are 8 in there, there's no openings for any other electrons or any other thing to happen. Therefore, it is stable and it doesn't react with any other type of atom. But in the body, there's actually reactive elements. In other words, elements that want to react with other elements to form these molecules. So the valence shells, the outer shells, are not full. Therefore, there is room for them to interact with another element. So looking at hydrogen, notice the hydrogen has 1 proton and 1 electron. Therefore, its outer element, or its outer shell is not full. It can hold up to 1 more, or it can do something with the 1 that it has. Carbon is a great example, again, the backbone of organic molecules. Notice carbon has 6 protons, 6 neutrons, therefore it has 6 electrons. Now, where are those 6 electrons? Well, we see 2 in the inner orbital, therefore there are 4 left over in the outer orbital. But the octet rule, or rule of 8, says that we want to have 8 electrons in the outer orbital, or the valence shell. Since we have 4, that means there are places for 4 more electrons. Therefore, we know that we'll actually have 4 bonds when we deal with carbon. We look at oxygen, its atomic number is 8, meaning that it has 8 protons and also 8 neutrons and also 8 electrons. In this situation, what we see, though, is we see that we have 2 electrons in the actual center, or in the inner orbital, and then we have 6 left over in the outer orbital, or the valence shell. And so, since there are 6 in the outer shell, we know it can hold up to 8. Therefore, there are 2 places left over, and therefore oxygen can bond with 2 things. Sodium, which is a relatively large element, something that's super important in the body, we will talk about. Notice that it actually has 11 protons. Therefore, it has 11 neutrons, or in this case 12 neutrons, but it has 11 electrons. So where are those electrons? Well, we see that there are 2 electrons around the nucleus. There are 8 in the next orbital, but our valence shell, or outer orbital, only has 1. This creates a problem because we would like to have 8 in our outer orbital or valence shell. So something's got to happen to that 1 electron, and we will talk about that. We see it forming in the body with sodium and chloride, but with other. Here we